I will just start my presentation. First, I would like to remind you probably about the idea of speculative program execution and how we adopt it in the speculative layer to support query execution. Then I will show you the new strategy I propose in this paper to make the speculative layer work better. I will show the experimental results verifying the idea, and I will end with a few words of conclusion. So, in general, a speculative execution is a method to parallelize computation when there are dependencies which make instruction parallel execution impossible. In such case, speculative computations would break this execution in a parallel way using some speculatively assumed data, which of course has to be found somehow, probably by guessing if we are clever, or simply determined by some special computation which are performed in advance. To obtain this speculative data, usually there are new type of computational threads called speculative threads, which are created at the basic program runtime. These threads implement the speculative computations we need aside to the primary program computations. In some point of program execution, when the primary input data or control states corresponding to these speculative values become available in the basic part of the program, a process of verification, of speculation verification must be performed, which would compare the assumed speculative data with their equivalent counterparts which were generated in the basic program. If we are lucky, the positively verified speculative threads are validated, and their results would be taken as output data of the executed program, which would be, of course, very beneficial for our execution. And based on this idea, we proposed a speculative layer, which is actually a middleware layer, which is situated between user application sending queries and actual relational database management system, which is supposed to answer those queries. The cooperation between the speculative layer and the RDBMS is based on permanent analysis of arriving user queries, which form a queue waiting for answer. This analysis is based on a special structure called a speculation window, which is actually a sliding window of user queries. Looking at these queries closed in that speculation window, we perform the process of speculative analysis, which is supposed to determine the speculative queries which would be executed for the current contents of that speculation window. That speculative analysis is the core of the speculation layer. To perform it beneficially, we create a graph representation of user queries. First, we create graphs of each user query, then we combine them together to create a joint representation of all the user queries contained in that SW. This joint representation is not a graph, it's a multi-graph. Then we analyze this query multi-graph and convert it into its extended version. That extension means that we add new edges to this query multi-graph called speculative edges, which are supposed to represent some important query features, which then are taken into account in the optimized speculative query generation. Here you can see an example of such query multi-graph. There are 3 user queries represented here. We can see different types of vertices representing relations, attribute, and values from the user queries. They are joined with edges also of different types depending where the attribute or value appeared in the user query. And we can also see the additional edges, this represented with dotted lines, so it's actually a speculative query multigraph, which already represent 2 speculative queries that could be generated for this particular graph. So what is a general scheme of action of the speculative layer? We look at this query multigraph. We perform a speculative analysis, which introduce new type of edges to this graph. And finally, a set of speculative queries is generated, which should be executed to produce results which then are useful for particular user queries. Then, when we already have that list of possible speculative queries, for each contents of that speculation window, 2 types of actions are performed concurrently. First, we execute the top query from the SW, so the first user query that now waits for the answer. We call it the non-speculative query. And what is very important, this non-speculative query should, or we want it to use some of the speculative query results which we have already prepared. So we adapt it to use the speculative query results if only we can. And the second type of action is execution of speculative queries, which we choose from the already generated list. And that selection is done based on some defined usefulness metrics. For now, you should know we take under consideration first the size of the results, so we don't want it to copy too much data. And second, we consider how many user queries can use its results, so we want it to be as useful as possible. After the non-speculative input query is executed, the speculation window moves on the stream of input queries by 1 query. So the representation of the executed user query in that multigraph is replaced by the representation of the next user query from the input query queue, and we repeat the process. So we perform the speculative analysis, we execute non-speculative query and some speculations, and so on. Now, in the old execution strategy, the non-speculative query was always the first query in the SW. That means a speculation window. This way, we kept the execution order of user queries, risking that for some of them, probably the speculative results might not be ready yet. With a new strategy, we allow the non-speculative query not to be the first one in the speculation window. And we do it in case when that first query would be executed without the use of speculative results. In such case, the next query in the SW, which can be executed with use of the already obtained speculative query results becomes our non-speculative query. And the first query in the speculation window has to wait, hoping that in the next step we would have a speculation for that query. This way, the speculative algorithm gets a chance to prepare and execute new speculative query, useful for the delayed user query. And we hope that the expected execution time reduction provided by the use of the speculative results would outweigh the potential execution delay of that user query. This is the picture representing that strategy. We can see the example of a speculation window which contains 5 user queries with ID the second, 3, 4, 5, and 6. We can see that the query, user query 2, has no speculative queries assigned, so there is nothing prepared for her. The query, user query 3, has 2 speculations ready for use. Number 4 has 1, and number 5 has also 1. So in such case, we would skip the user query 2, execute non-speculatively query number 3 using one of those speculations. And of course, in parallel, we would execute probably some 2 new speculative queries, 6 and 7, expecting that at least one of them would be assigned to user query 2. We have verified that idea experimentally. We use database structure and data generated generated from the TPC benchmark. Additionally, we prepared user query templates, 7 of them. Each of them is modeling a user query which is referencing 2 to 5 database relations. Based on those templates, 3 sets of 1000 user query each was generated with random values for the conditions appearing in its where clauses. And what experiments show us? The first chart presents the execution time of queries of each template and how they are affected if we manage to execute such query using speculative results. The red bars present the execution time of user query without the use of speculation results, and the rest of colorful bars present the reduction obtained. For example, that navy bar present the execution time of a query of template 5 if we manage to use 2 speculative query results for each user query. What we can see that each speculative query used provides further reduction in the user query execution time. It's especially visible for templates T5 and T7, which have considerably longer original execution times, because T5 is approximately 163 seconds and T7 is 181 seconds. So for such queries, speculative results provide significant reduction in execution time. The experiments, the first series of experiments was conducted for the speculation window size 5. You could wonder why is it 5. In the very beginning of the development of the speculative layer, we ran a series of experiments to verify the possibly optimal size of the speculation window, and back then it turned out to be useful, to be performing well when it was size 5. Bigger speculation window didn't provide further improvement in the query execution. So we, for now, we stick with the size 5. And the new strategy, apart from the reduction in the execution time, also reduced the number of user query executed without the use of the speculative results, because we allowed to delay such queries from approximately 113, which was about 10% of the test set, to 57. The query order change was reported 132 times and concerned 58 user queries. So we can see that some of user queries were delayed more than once. And the maximal delay of the first query in the speculation window execution was 4. And the average delay was equal approximately to 59. That was the first series of experiment. But after that, let's call it basic execution, I decided to run a series of experiments to verify if that new strategy influences that already fixed speculation window size. Maybe now it's not 5 anymore and should be 8, for example. And these are the obtained results for the SW sizes from 5 to 15. What we can see here, we can see that the growing size of the speculation window, the number of the no job reports is also growing significantly, up to 232 for SW size 15. What is that no job report? This is the case when for a particular speculation window and a particular multigraph, there is no new speculative query generated to be executed. That happens especially for bigger sizes because you should remember that each move of SW removes one user query from the graph representation and adds new one, so far one. So when the graph is big, and the bigger the speculation window is, the bigger the graph is, the query, the graph queries, the graph structure change is not enough to emphasize certain vertices. So it's not enough to generate new and unique speculative query for execution. And that is not very good observation. Thus, we can see, it's a consequence of that no job, that the total number of executed speculative queries here is actually decreasing with the bigger sizes of speculation window. Even more even though that each executed speculative query is assigned to more user queries for potential use, here we can see it's growing from 198 to 356. It doesn't influence and preferably reduce the number of user queries executed without the speculative support. 4 bottom rows of this table present results characteristic for the new execution strategy. So we can see what happens when we skip user queries and delays the execution. And we can see that the number of the user queries whose execution were delayed varies around 60 here. up to 70, and doesn't seem to be dependent on the SW size. However, the bigger SW gets, the execution delay of such queries grows. And here it grows up to 13 steps for SW size 15. No, which is not very advantageous feature, because the too long delays would require probably some kind of new mechanism which would prevent query starvation, not included in this execution, when the waiting time would predominate the potential benefits from using the speculative query results. So based on these results, we say that the speculation window size 5 was the optimal choice for the execution strategy so far. So to conclude, we present the new strategy for the non-speculative query execution in the speculative query execution support system called the speculative layer. That new strategy allows the change of the order of user queries execution in case when the first query in the speculation window would have to be executed without the use of the speculative results. With this new strategy, almost 95% of user queries were executed with the use of at least one speculative query results, providing the query average execution time reduction approximately 2 times shorter. The execution order change was reported for approximately 58 queries, which is like 5% of the queries set, with the maximal execution delay of 4 queries. And the second series of experiments proved that the adopted parameter, which is the speculation window size equal 5, is still a good choice. What then? The further work will focus on the development of an even more flexible user query execution strategy for a speculation window. There is already a concept of a variable shift speculation window that should be considered. We should probably consider the chance to execute more than one user query non-speculatively for each SW. That maybe if 2 or 3 user queries in one speculation window already have speculations ready for use, why not execute them and make a move of 3 user queries this time? Okay, that's all I have. Thank you very much.
Thank you. Any questions? So I have some. You have said that the speculation window size 5 is the best.
So far, at least.
And what if it would be shorter? Not longer, but shorter. 4, 3.
We performed such tests at the beginning of the work on the speculative layer, and growing size up to 5 was providing more speculations that were generated, useful for more user queries.
Okay.
If we would consider such small windows like 2, we could create and execute speculation which would be useful maximally by 2 user queries. with the 5, we can obtain, at least theoretically, speculation useful for 5 user queries. Unfortunately, with the size 10, we didn't obtain speculation useful for 10 user queries.
Okay. Okay, and one more. The reference times to which you compared your results were not sequential queries, or were it sequential execution?
No.
And you didn't
Try to execute sequentially the whole set?
Yes, yes.
No.
I think it would be quite interesting to compare it to such.
Yes, yes.
Okay.
Thank you very much.
Thank you very much, Ania.